What if everything we thought we knew about the movement of celestial bodies was just the tip of the cosmic iceberg? Picture the night sky not as a predictable clockwork of orbits, but as a dynamic, ever-changing dance where the rules are being rewritten before our eyes. For centuries, astronomers relied on Newton's laws and Kepler's equations to map the heavens. But now, 38 jaw-dropping discoveries in celestial mechanics are tearing up the old playbook. These aren't minor adjustments, they're revolutions that reveal planets behaving like cosmic rebels, black holes waltzing in pairs where they shouldn't, and entire star systems moving in ways that defy conventional physics. Think about the last time you gazed up at the stars and felt that sense of wonder. That awe is about to deepen because what scientists are uncovering today goes beyond textbook explanations. Imagine a planet ejected from its solar system, racing through the galaxy like a lone wanderer, or two supermassive black holes locked in a gravitational embrace so precise, it's as if they're following a rhythm we can't yet hear. These aren't science fiction scenarios, they're real phenomena documented in the latest research, and they're forcing us to rethink the very foundations of how objects move through space. This video is your front row ticket to the most thrilling updates in modern astrophysics. We'll explore how these 38 discoveries are unraveling mysteries about gravity's true nature, why some orbits seem to break the rules, and what it all means for our understanding of the universe's grand design. By the time we're done, you'll see the cosmos not as a static backdrop, but as a living, breathing entity full of surprises. So buckle up, we're about to journey into the heart of celestial mechanics, where every revelation promises to reshape what you thought was possible. When Oumuamua streaked through our solar system in 2017, it wasn't just another space rock, it was a cosmic enigma wrapped in mystery. This cigar-shaped interstellar visitor didn't behave like anything we'd seen before. As it hurtled past the sun, astronomers expected it to slow down predictably under gravity's pull, but instead, it did something extraordinary. It sped up. This wasn't a subtle nudge, it was a clear, unexplained acceleration that sent shockwaves through the scientific community. At first, researchers thought maybe outgassing the release of gases from a comet's surface could explain the boost. But here's the catch. Oumuamua showed no signs of a coma, the glowing cloud of gas and dust that typically surrounds active comets. No tail, no icy debris, nothing. So if it wasn't outgassing, what invisible hand was pushing it forward? Some theorists proposed exotic possibilities, like hydrogen ice sublimating in deep space, a process we've never observed before. Others dared to ask an even wilder question. Could Oumuamua be artificial? A solar sail or probe from another civilization, catching sunlight like a cosmic kite? While the alien technology idea grabs headlines, the real revelation lies in the data. Oumuamua's acceleration challenges our fundamental understanding of how objects move through space. If natural forces we've never accounted for can alter an object's trajectory this dramatically, what else might be out there, hidden in the darkness between stars? This single visitor has forced astronomers to rethink the playbook for interstellar objects, suggesting the universe might be far stranger and far more dynamic than our textbooks ever imagined. The implications ripple across astronomy. If Oumuamua's behavior isn't a fluke but a sign of broader, unknown physics, future interstellar visitors could upend our models entirely. Imagine a galaxy where objects don't just follow gravity's rules but dance to a hidden tune we're only beginning to hear. Every peculiar motion, every unexplained speed boost could be a clue, a whisper from the cosmos that there's so much more to learn. And that's the thrill of Oumuamua. It didn't just pass through our solar system. It left us with a question mark hanging in the sky, urging us to look deeper. These rogue stars are cosmic outlaws, breaking every rule we thought governed their escape. Hypervelocity stars were supposed to be the universe's ultimate straight shooters, flung from galaxies at speeds over 1,000,000 miles per hour, never to look back. Their trajectories should have been simple, predictable lines, like bullets fired into the void. But something extraordinary is happening. Telescopes have captured these stellar fugitives, not racing away in clean arcs, but mysteriously curving, as if tugged by invisible hands. The moment astronomers spotted the first bend in a hypervelocity star's path, it sent them scrambling for explanations. One leading theory points to dark matter, the universe's elusive, invisible scaffolding. Could pockets of this mysterious substance be warping space in ways we can't directly see, rerouting stars like cosmic detours? Another possibility ripples through the scientific community: gravitational waves. These faint tremors in spacetime, first detected in 2015, might carry enough hidden energy to nudge stars off course over vast distances. Imagine a stone skipping across a pond, its path altered by unseen waves. Now picture that on a galactic scale. But perhaps the most startling implication is what this means for how galaxies expel stars in the first place. The traditional ejection model reads like a simple cosmic slingshot. A star ventures too close to a supermassive black hole at a galaxy's core, gets whipped around by gravity's whip, and hurtles outward. Yet these curved trajectories suggest forces at play. We've never accounted for forces that might rewrite how we understand galactic dynamics. Could black holes be flinging stars with a hidden spin, like a pitcher throwing a curveball? Or are entire galaxies surrounded by dark matter halos so complex they bend even the fastest escapees? Every twisted path these stars take is a breadcrumb leading to deeper questions. If hypervelocity stars aren't obeying the old rules, what else in our cosmic neighborhood might be moving in ways we've failed to predict? This isn't just about rewriting textbooks, it's about realizing the universe has been playing a far more intricate game, and we're only beginning to learn the rules. Black holes don't just collide, they tango. For decades, scientists assumed binary black holes moved in orderly, predictable orbits, locked in a celestial waltz dictated by Einstein's equations. But the universe loves a plot twist. Recent observations have caught these cosmic heavyweights breaking formation, their paths spiraling into chaotic, non-Keplerian patterns that defy every expectation. Instead of clean ellipses, their orbits resemble scribbles, wild, unpredictable, and utterly mesmerizing. So what's throwing these gravitational giants off their scripted dance? One compelling theory points to the fabric of spacetime itself. Imagine a trampoline sagging under two bowling balls. Normally, they'd roll toward each other in smooth curves, but what if the trampoline had hidden folds or ripples? That's the idea behind higher dimensional effects, subtle warps in reality we can't yet measure, nudging black holes onto bizarre new trajectories. Some physicists speculate these anomalies might be glimpses of extraspatial dimensions, hidden layers of the universe where gravity behaves in ways our 3D brains can't quite picture. Then there's the dark matter wildcard. Could invisible halos of this mysterious substance be tugging on black holes like cosmic puppet strings? Or perhaps gravitational waves, ripples from distant collisions, are washing over these systems, leaving behind faint but detectable disturbances? The most tantalizing possibility, that we're seeing cracks in general relativity itself. Einstein's theory has held up spectacularly for over a century, but black holes are the ultimate stress test. If their movements refuse to follow the rules, even here in the extreme gravity club, it could mean the laws we've written aren't just incomplete, they're missing entire chapters. The implications ripple far beyond theoretical physics. If black hole binaries don't move as predicted, it could throw a wrench into our models of galaxy formation. These pairs are thought to be the engines behind some of the universe's most energetic events, from quasar outbursts to gravitational wave bursts. A single misbehaving duo might not append cosmology, but a pattern of them. That's a revolution waiting to happen. Every erratic orbit is a breadcrumb hinting at forces or dimensions we've yet to name. And that's the beauty of this discovery. It's not just about rewriting equations. It's about realizing the cosmos still has moves we haven't even begun to learn. We've long imagined planetary systems as cosmic clockwork, with planets ticking along predictable orbits like gears in a machine. But the universe has just unveiled a breathtaking new rhythm, entire families of exoplanets moving in perfect celestial harmony. These aren't just random arrangements, they're orbital resonance chains where planets synchronize their dances with mathematical precision so exact, it's as if the cosmos itself composed a symphony. Take the star system TRAPPIST-1, where 7 Earth-sized worlds orbit in a staggeringly precise chain. For every 2 orbits one planet completes, its neighbor circles exactly 3 times. The next pair, 3 to 4, this pattern cascades through the entire system like a gravitational melody, with each world locked in perfect step. What's astonishing isn't just the beauty of this harmony, it's the fact that such delicate arrangements were long thought impossible. Conventional models predicted these intricate resonances should unravel over time, disrupted by gravitational nudges or cosmic collisions. Yet here they are, defying expectations with their flawless coordination. So how does nature orchestrate these perfect alignments? One theory suggests these systems formed far from their host stars, where cooler temperatures and gentler dynamics allowed planets to settle into resonant grooves early on, like marbles finding the smoothest path down a slope. Another idea points to tidal forces, the gravitational tug of war between planets and their stars, acting like cosmic metronomes, slowly tuning orbits into sync over billions of years. But the most tantalizing possibility, that some unseen external force, perhaps a passing star or lingering gas disk, reached in and fine-tuned these systems like a master conductor. The implications ripple far beyond aesthetics. Resonance chains act as cosmic forensic tools, offering clues about a system's violent youth. The precision of these arrangements suggests many exoplanet systems avoided the chaotic scattering we see in our own solar system, where Jupiter's migrations likely flung debris wildly. Instead, these worlds must have migrated inward with extraordinary gentleness, sliding into place like pieces of a gravitational puzzle. Yet the biggest revelation might be what this means for planetary habitability. In systems like TRAPPIST-1, resonant orbits create stable temperature zones, shielding planets from extreme swings that could sterilize their surfaces. It's as if the universe engineered these rhythms not just for beauty, but for balance, a subtle hint that the conditions for life might be woven into the very fabric of celestial mechanics. Every new resonance chain we discover is a reminder the cosmos doesn't just move, it sings. Dark matter was supposed to be the universe's silent scaffolding, an invisible, motionless framework holding galaxies together. But the cosmos has a way of upending our assumptions. Cutting-edge observations now reveal dark matter as something far more dynamic, flowing through galaxies like cosmic currents and clumping in ways that rewrite the rules of galactic rotation. Where we once pictured a static halo, we now see rivers of unseen matter pulsing through space, tugging stars onto paths that defy prediction. Take the Milky Way's neighbor, the Triangulum Galaxy. Its outer stars rotate at speeds that should send them flying into the void, yet something keeps them tethered. Traditional models blamed a stationary dark matter envelope, but new data shows something astonishing. These stars aren't just being held, they're being steered. Their orbits align with dark matter streams as if riding invisible rails. This isn't the behavior of a passive substance. It's the fingerprint of an active, almost fluid-like force. The implications send shockwaves through astrophysics. Cold dark matter, the long-standing theory that this mysterious substance moves sluggishly, now faces serious challenges. If dark matter flows, clumps, and interacts in ways we never anticipated, entire simulations of galaxy formation might need recalibration. Some theorists propose warm dark matter with lighter, faster-moving particles. Others explore self-interacting dark matter, where these unseen particles nudge each other like dancers in a crowded ballroom. The boldest ideas suggest dark matter might even have its own hidden forces, a shadow physics operating beyond our detection. Yet the most thrilling part isn't just the chaos, it's the clues. Every rogue star cluster, every warped galactic disk is a breadcrumb pointing toward dark matter's true nature. These rivers and clumps could be the key to unlocking why galaxies spin as they do, why some stars move in flocks while others stray, and perhaps even how the universe stitches itself together on the grandest scales. What we're witnessing isn't just a revision of theory, it's the birth of a new understanding, one where the invisible hand shaping our cosmos is far more alive than we ever dreamed. Neutron stars have always been the universe's ultimate tightrope walkers, balancing crushing gravity against explosive internal forces in a precarious cosmic dance. But now, astronomers have caught them doing something even more bizarre, glitching. These sudden, unpredictable jumps in spin rate were once thought to be isolated hiccups, like a skipping record in the depths of space. The shocking new revelation, these glitches aren't random at all. They're synchronized with gravitational waves, the faint ripples in spacetime first detected in 2015. It's as if every time one of these ultra-dense stars stumbles, the universe itself echoes the misstep. Picture a neutron star's interior like the world's most extreme physics experiment. A single teaspoon of its material would weigh 1 billion tons on Earth, with protons and electrons crushed together into a swirling quantum soup. Under that unimaginable pressure, the star's crust, a crystalline lattice just centimeters thick, behaves like a cosmic eggshell. When internal stresses build, the crust cracks, causing the entire star to suddenly spin faster. That's the glitch, but here's where it gets wild. Advanced detectors like LIGO and Virgo have now captured gravitational waves pulsing outward at the exact moment these spin jumps occur. The correlation is so precise it can't be coincidence. What's really turning heads is what this means for our understanding of matter itself. Neutron stars may be acting as natural particle accelerators, revealing quantum behaviors that no lab on Earth could replicate. Some theories suggest these glitches unleash avalanches of superfluid vortices, whirlpools of frictionless neutrons, suddenly unlocking and surging outward. Others propose cracks in the crust generate shockwaves that ripple through spacetime itself. The most radical idea, that we're seeing hints of exotic particles or unknown forces at work in these extreme conditions. Phenomena that only reveal themselves when matter is pressed beyond anything we can simulate. The implications stretch far beyond these stellar oddities. If gravitational waves can trace the inner workings of neutron stars, we've essentially been handed a new telescope, one that peers not with light, but with vibrations in the fabric of reality. Every glitch becomes a message, carrying secrets about how matter behaves when the rules of ordinary physics break down. And with thousands of neutron stars scattered across the galaxy, each one a potential laboratory, we're standing at the threshold of discoveries that could rewrite our playbook for the entire universe. These aren't just celestial hiccups, they're cosmic telegrams, and we're finally learning how to read them. Rogue planets were supposed to be the universe's loners, dark, drifting worlds exiled from their parent stars, moving through the void with no one to answer to. But something extraordinary is happening to these cosmic nomads. Instead of coasting through space at steady speeds, astronomers have caught them accelerating as if pushed by invisible hands, gaining velocity without any discernible cause. These aren't subtle shifts. Some of these wanderers have been clocked speeding up by thousands of miles per hour over just a few decades, defying every expectation of how isolated objects should behave. So what's giving these planets a cosmic kick? One theory points to microscopic black holes, specks of collapsed matter too small to detect directly, yet dense enough to exert gravitational pulls as they zip through space. Imagine a rogue planet passing near one of these invisible pinpricks of gravity, getting a slingshot boost like a stone skipping off a pond's surface. Another possibility dives into the realm of dark energy, the mysterious force accelerating the universe's expansion. Could pockets of this repulsive energy be concentrated enough to nudge individual planets, acting like unseen currents in the interstellar sea? Then there's the wild card, primordial gravitational waves. These ripples in space-time, left over from the Big Bang, might still be washing through the cosmos like echoes of creation. If a rogue planet happened to surf one of these ancient waves, it could gain momentum without any visible interaction, a ghostly push from the universe's earliest moments. The most tantalizing idea, that we're seeing hints of an entirely new force, one that only manifests in the extreme isolation of interstellar space, where the usual rules of gravity and motion don't quite apply. The implications are staggering. If these rogue planets are being accelerated by unseen phenomena, it means the emptiness between stars isn't empty at all. It's alive with hidden forces waiting to be discovered. Every unexplained speed boost is a clue, a breadcrumb leading us toward a deeper understanding of the universe's invisible machinery. And with new telescopes coming online capable of tracking these lone wanderers with unprecedented precision, we might soon crack the code behind their mysterious movements. The cosmos has always been full of surprises, but these rogue planets are proving that even in the darkest, most isolated corners of space, the universe still has secrets to spill. Spiral galaxies have always been the crown jewels of the cosmos. Those majestic pinwheels of stars we assumed were held together by dark matter's invisible grip. But nature loves a good paradox. Astronomers have now found galaxies like NGC 1052 and DF2 that spin with perfect coherence, their outer stars whipping around just as fast as the inner ones, yet they contain almost no dark matter at all. This isn't just a missing piece of the puzzle, it's the puzzle flipping over to reveal an entirely new picture on the back. For decades, dark matter was the go-to explanation for why galaxies don't fly apart. The math was clear. Visible stars and gas alone couldn't generate enough gravity to maintain those elegant spiral arms. Something unseen had to be anchoring them, something making up over 80% of the universe's matter. But these newly discovered galaxies turn that logic on its head. Their rotation curves, the speed at which stars orbit the center, follow the same smooth patterns as dark matter-rich galaxies, yet when researchers tally up the mass from visible stars and gas, it accounts for nearly all the gravity needed. No dark matter required, so how does a galaxy defy the rules? One camp of physicists argues this points to flaws in our understanding of gravity itself. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently at extremely low accelerations like those in a galaxy's outskirts. It's as if the universe has a hidden toggle switch, making gravity stronger where we least expect it. But MND has its own gaps, struggling to explain cosmic phenomena like the bullet cluster, where dark matter's gravitational fingerprint is unmistakable. Others suggest these galaxies might be the aftermath of a cosmic heist, places where dark matter was violently stripped away by collisions or tidal forces, leaving behind a gravitational, ghost imprint that still shapes stellar motions. Imagine a sculptor removing their hands from clay, yet the sculpture holds its form momentarily. The most radical idea, that dark matter isn't a single substance but a family of particles, some invisible to our current detectors, with certain galaxies preferentially losing or never accumulating certain types. The implications ripple far beyond a few oddball galaxies. If dark matter isn't the universal glue we thought, entire chapters of cosmology might need revision. From galaxy formation simulations to our models of the universe's expansion, the foundations of modern astrophysics could be shakier than we realized. Yet therein lies the thrill. Every rule-breaking spiral is a clue, hinting that the cosmos still has cards up its sleeve. Whether it's rewriting gravity or redefining dark matter, one thing's certain: the universe is far more inventive than our textbooks gave it credit for. Quantum mechanics and celestial motion were supposed to live in separate universes, one governing the realm of atoms, the other ruling planets and stars. But nature loves to blur boundaries. Scientists have now detected something astonishing. Satellites orbiting Earth are being ever so slightly nudged off course by nothingness itself. That's right, the quantum vacuum, once thought to be empty, is teeming with particles that flicker in and out of existence, and these ghostly fluctuations are leaving fingerprints on the paths of spacecraft hundreds of miles above our heads. Take the LEGIO's satellites, a pair of orbiting reflectors used to measure Earth's rotation. Over decades of precision tracking, researchers noticed their orbits decaying faster than atmospheric drag alone could explain. The discrepancy was tiny, less than a millimeter per year, but the implications were massive. After ruling out every conventional cause, from solar radiation to residual gases, physicists landed on a radical explanation: virtual particles. According to quantum theory, empty space isn't truly empty. It's a seething foam where particle-antiparticle pairs spontaneously emerge and annihilate in fractions of a second. These fleeting disturbances warp spacetime itself, creating microscopic ripples that, when summed up over vast distances, could subtly alter a satellite's trajectory. This discovery shatters an old assumption that quantum effects cancel out at macroscopic scales. Instead, we're seeing the quantum world whisper to the cosmos, its influence scaling up in ways we never anticipated. Some theorists suggest these vacuum fluctuations might act like cosmic potholes, gently scattering satellites as they pass through regions of heightened quantum activity. Others propose even wilder ideas. Could certain orbital anomalies be signatures of hypothetical particles like actions, or evidence of extra dimensions crumpling spacetime at scales we've only begun to probe? The most profound implication isn't just about satellites, it's about rewriting the hierarchy of physics. If quantum jitters can nudge a 1,000-pound spacecraft, what else might they be influencing? Planetary orbits, star clusters, the rotation of entire galaxies. We've long treated celestial mechanics as a purely classical domain, but the universe is reminding us there are no closed systems. From the tiniest quantum flicker to the grandest galactic dance, everything is connected in ways we're only starting to glimpse. And that's the beauty of this discovery. It's not just solving a mystery about orbital decay. It's revealing a cosmos far more entangled, far more mysterious than we ever dreamed. Trojan asteroids have long been considered the solar system's faithful companions, cosmic hitchhikers riding in the gravitational sweet spots ahead of or behind planets, locked in celestial harmony. These Lagrange points were thought to be nature's parking spaces where objects could remain stable for billions of years. But new observations reveal a startling truth. Many of these Trojans are misbehaving, drifting from their expected positions with movements that defy our most careful calculations. Take Jupiter's Trojans, for example. These ancient asteroids, numbering in the thousands, share the gas giant's orbit around the Sun, clustered around its leading and trailing Lagrange points like a celestial entourage. For decades, astronomers assumed these configurations were set in stone, or rather, set in space. Yet recent tracking data shows some of these asteroids wobbling, their orbits shifting unpredictably over surprisingly short timescales. Some have even been caught migrating between Lagrange points, as if hopping between invisible gravitational islands. What's causing this instability? One leading theory points to subtle gravitational nudges from other planets, particularly Saturn. While Jupiter dominates its orbital neighborhood, Saturn's periodic tugs, like a distant drummer setting an irregular beat, might be enough to disrupt these delicate balances. Another possibility involves the asteroids themselves. Many Trojans aren't solid monoliths but loose rubble piles, their shapes irregular and their densities uneven. As sunlight pushes against their uneven surfaces over millennia, a phenomenon called the Yarkovsky effect, their paths could subtly drift like leaves carried by a faint breeze. The most tantalizing explanation, though, involves chaos theory. The solar system isn't a perfect clockwork mechanism. It's a dynamic, ever-evolving dance where tiny perturbations can snowball over time. Even in seemingly stable Lagrange points, gravitational resonances and hidden instabilities might lurk, waiting to surface after eons of quiet. This means our solar system's architecture isn't just evolving, it's rewriting its own rules on timescales we're only beginning to measure. The implications reach far beyond a few wandering asteroids. If Trojans can destabilize, it challenges our assumptions about how planetary systems settle into long-term stability. Exoplanet researchers now question whether similar Lagrange points in distant star systems might also be less reliable than we thought. And closer to home, it forces us to reconsider the very nature of gravitational balance, not as a fixed state, but as a fleeting moment in an endless cosmic reshuffling. These drifting Trojans aren't just celestial curiosities. They're messengers telling us that even the quietest corners of our solar system are alive with motion, and nothing in space stays still forever. Pulsars have long been nature's most precise cosmic clocks, spinning neutron stars that beam radio waves with metronomic regularity, some keeping time better than atomic clocks on Earth. But these celestial timekeepers are now revealing something far grander. The universe's background hum of gravitational waves rippling through space-time on scales so vast they stretch our imagination. Imagine throwing a pebble into a pond and watching the ripples spread, except this pond is the entire galaxy, and the pebbles are supermassive black holes merging in the cosmic deep. This discovery comes from pulsar timing arrays, global networks of radio telescopes tracking dozens of these spinning stars across the Milky Way. By comparing the arrival times of their pulses over decades, scientists have detected subtle discrepancies, some arriving a fraction of a second early, others late, in patterns that betray the passage of gravitational waves warping the space between us and the pulsars. These aren't the high-frequency chirps from stellar mass black hole mergers that LIGO detects. These waves are monsters with wavelengths so long, it takes years for a single undulation to pass by, generated by black holes billions of times the sun's mass dancing in slow motion across the universe. The implications rewrite cosmic mechanics as we know it. These waves don't just ripple past objects, they slightly compress and stretch the very fabric through which planets, stars, and galaxies move. Picture a grid of spacetime not as a static stage but as a dynamic trampoline, forever vibrating under the footsteps of distant black hole behemoths. Every orbit in the galaxy, from Earth around the Sun to stars circling the Milky Way's core, is subtly influenced by this endless cosmic surf. What's truly startling is the scale of the disturbances. Some of these waves likely originate from pairs of supermassive black holes that never fully merge, stuck in a gravitational stalemate just light years apart. Their eternal waltz generates a cacophony of low-frequency waves that overlap and interfere, creating a stochastic background, a gravitational wave chorus humming beneath everything. Others might be echoes from the early universe, relics of collisions that shaped the cosmos itself. This discovery doesn't just add another layer to astrophysics, it hands us an entirely new sense with which to perceive the universe. Just as light reveals stars and radio waves unveil hidden gas clouds, gravitational waves now expose the invisible choreography of spacetime itself. And with every pulsar added to these arrays, we sharpen our ability to listen to the cosmos' deepest rhythms, uncovering a universe far more dynamic and interconnected than we ever dared to dream. Moons were supposed to follow the rules tidally locked to their host planets like obedient dancers, always showing the same face as gravity's grip sapped their spin. That's how it works in our solar system, where even mighty Jupiter couldn't keep volcanic Io or icy Europa from falling into sync. But the universe loves an exception. Astronomers have now spotted exomoons hundreds of light years away that refuse to play by these cosmic conventions, spinning freely as if tidal forces barely touch them. These aren't just oddballs, they're revolutionaries, forcing us to rewrite the playbook on how moons and planets interact. Take Kepler 1625b's moon, a world roughly the size of Neptune orbiting a gas giant in a distant star system. By all rights, its rotation should have locked eons ago, yet measurements reveal it pirouettes independently, with days and nights cycling across its surface. The leading theory, a hidden ocean kilometers deep, sloshing beneath an icy shell. On Earth, our moon's pull creates tides in our oceans, but flip that scenario, imagine an exomoon where the planet's gravity tugs on a global sea instead of solid ground. That liquid layer could act as a buffer, allowing the outer crust to spin freely while the interior gradually sinks. It's like a greased bearing in a cosmic gearbox, reducing friction between layers and defying the inevitable lock. But oceans aren't the only explanation. Some of these rogue rotators might harbor internal heat sources, radioactive cores, or residual formation energy, stirring up enough geologic activity to resist synchronization. Picture a moon with constant volcanic upheaval, its surface reshaped by eruptions that redistribute mass like a figure skater adjusting their arms to control a spin. Others might owe their freedom to chaotic orbits, influenced by additional planets or stars in their systems that keep gravitational forces in flux. The implications shake the foundations of planetary science. If moons can retain independent rotation, it means they're far more dynamic than we imagined, not just passive rocks, but worlds with their own internal engines driving weather, tectonics, and even potential habitats. A spinning moon could distribute heat more evenly, preventing the extreme temperature swings that render one side scorching and the other frozen. For astrobiologists, that's a game changer. These rebellious rotators might be prime candidates in the search for life beyond Earth. Yet the biggest revelation is what this means for tidal theory itself. We've long treated synchronization as inevitable, but these exomoons prove celestial mechanics is messier and far more inventive than our textbooks suggested. From subsurface oceans to gravitational chaos, nature has found loopholes in the rules we thought were universal. And that's the thrill of discovery. every rule-breaking moon isn't just an anomaly. It's a signpost pointing toward processes and possibilities we've only begun to explore. Our galaxy isn't just drifting through space, it's being hauled toward something unseen with unimaginable force. For decades, astronomers have known about the Great Attractor, a mysterious gravitational anomaly pulling the Milky Way and thousands of nearby galaxies toward it at over 1 million miles per hour. But the plot thickens. This colossal tug is merely part of an even grander motion, a dark flow carrying entire superclusters toward some cosmic siren call beyond the edge of our observable universe. This isn't just about one invisible mass, it's about a fundamental rewrite of how we map the cosmos. Imagine floating in a river where the current grows stronger the farther you go, yet the source lies hidden around a bend you can't see. That's the enigma of dark flow. Measurements from galaxy surveys and cosmic microwave background radiation reveal thousands of galaxy clusters streaming in the same direction, as if drawn by a structure so vast it dwarfs anything in our cosmic neighborhood. The strangest part, this motion defies the uniform expansion of the universe. While most galaxies recede from us due to Hubble's law, these clusters move sideways, like leaves caught in a wind blowing perpendicular to the river's flow. What could possibly exert such influence? One radical theory points to a supermassive overdensity, a concentration of matter so enormous it warps spacetime on scales we've never observed. Picture a cosmic mountain range beyond our horizon, its gravity reaching across billions of light years to steer galaxies like celestial marionettes. Another possibility ventures into multiverse territory. Perhaps our universe isn't perfectly uniform after all, and neighboring bubble universes, if they exist, exert gravitational leakage at the edges, nudging our local cosmos askew. But the most humbling realization, this motion hints at structures so colossal, they challenge the cosmological principle, the idea that the universe looks roughly the same in all directions. If dark flow is real, it suggests an asymmetry in the grand cosmic tapestry, with threads woven on scales beyond our observational limits. Telescopes can't see past the observable universe's edge, but gravity doesn't respect that boundary. Every galaxy caught in this flow is a breadcrumb tracing a path to something we may never fully glimpse. The implications ripple through astrophysics. If such titanic structures exist, our models of cosmic inflation and large-scale formation need recalibration. From the distribution of dark matter to the very fate of the universe, this unexplained flow could be the first clue that the cosmos operates on a canvas far grander than we ever imagined. And that's the thrill of the chase. Sometimes the most profound discoveries aren't what we can see, but the invisible currents pulling us toward the unknown. Gravity is supposed to be the universe's great constant, the unwavering force that binds galaxies, shapes cosmic structures, and pins us to the ground. But what if it wasn't always this strong? Hidden in the light of quasars, those brilliant beacons from the universe's youth, astronomers have uncovered a startling pattern. The fingerprints of gravity itself may be changing over cosmic time. These ancient beams of light, traveling for billions of years before reaching our telescopes, carry subtle shifts in spectral lines that suggest gravity's grip wasn't always what it is today. The key lies in something called the fine structure constant, a number that governs how light interacts with matter. By studying how this constant appears in quasar spectra, researchers noticed something bizarre. Its value seems to vary depending on where and when we look. Some quasars show signatures that would only make sense if electromagnetism or gravity behaved differently in the distant past, the most radical interpretation. That the fundamental forces we consider immutable might actually evolve, weakening or strengthening over epochs. Imagine gravity as a dial on the universe's control panel, subtly turned over billions of years. In its early chapters, it could have been a fraction stronger, accelerating star formation and galaxy assembly, or slightly weaker, allowing matter to spread more freely. This isn't just tweaking a parameter, it's rewriting the foundational rules of physics. Einstein's general relativity assumes gravity's constancy. If that assumption cracks, entire theories about black holes, dark energy, and cosmic expansion might need reworking from the ground up. Skeptics argue these measurements could be illusions, dust clouds, or instrumental quirks mimicking spectral shifts. But the data keeps mounting. Independent teams analyzing different quasar populations have found similar anomalies, and when cross-checked with other cosmic probes like the cosmic microwave background, the patterns resist easy dismissal. The boldest theorists suggest we're glimpsing evidence of extra dimensions slowly unfurling or contracting, altering how gravity propagates through space-time on grand scales. If confirmed, this discovery wouldn't just add a footnote to astrophysics, it would redefine our place in the cosmos. A universe with variable constants is one where the laws themselves have a history, where the rules we take for granted are merely snapshots in an epic saga of change. It raises profound questions. Are today's physics just a temporary phase? Could gravity continue evolving, quietly shaping the universe's fate in ways we've yet to imagine? The answers might lie in the next generation of telescopes, poised to capture even older light and perhaps to reveal a cosmos far more dynamic than we ever dreamed. The heart of our galaxy is a cosmic maelstrom where stars shouldn't survive, let alone dance. Sagittarius, a star, the supermassive black hole anchoring the Milky Way, was expected to whip nearby stars into neat, predictable orbits like planets around the Sun. But reality paints a far wilder picture. Astronomers tracking these stellar daredevils have captured something astonishing. Their paths twist into braids and loops, crisscrossing in chaotic patterns that mock the orderly ellipses of textbook celestial mechanics. One star, S2, recently completed a 16-year orbit that took it within just 11 billion miles of the black hole's event horizon, a cosmic hair's breadth where space and time warp beyond recognition. Yet instead of following the predicted path, it veered off course as if tugged by invisible fingers, its trajectory kinking in ways general relativity can't fully explain. What's bending these stellar orbits into cosmic pretzels? The leading suspect is frame dragging, an effect where a spinning black hole literally twists the fabric of spacetime around it like honey stirred by a spoon. Sagittarius, a star's rotation might be so extreme, it's warping its surroundings into shapes we've only theorized. Picture a record player warping a vinyl disc. Now imagine that distortion affecting not just space, but time itself, altering how stars experience the passage of seconds as they plunge through these bent dimensions. Some simulations suggest the black hole's spin axis could even be wobbling, creating a gravitational gyroscope that sends stars spiraling in ever-shifting patterns. But frame dragging alone might not tell the whole story. Another possibility lurks in the darkness, an unseen second black hole. Binary supermassive black holes are thought to be rare, yet their gravitational duet could explain the erratic stellar motions. If a smaller black hole orbits Sagittarius, a star, closely enough, its kicks could send stars veering off course like billiard balls struck by an invisible cue. There's also the dark matter wild card. Could invisible halos of this mysterious substance be clustering near the galactic center, adding extra tugs to the already chaotic dance? The implications reach far beyond our galaxy's core. If Sagittarius, a star's spin, is rewriting orbital rules, it challenges how we model black holes across the universe. Current templates assume relatively stable rotations, But what if many supermassive black holes are spinning faster or more unpredictably than we thought? That could reshape our understanding of galactic evolution, quasar outbursts, even the gravitational wave background humming through the cosmos. Every braided star path is more than a curiosity. It's a clue, hinting that the universe's most extreme environments don't just bend the rules. They rewrite them entirely. Dark energy was supposed to be the universe's steady hand, an unchanging force accelerating cosmic expansion at a constant rate. But the cosmos thrives on surprises. Cutting-edge observations now reveal dark energy as something far more unpredictable, its strength waxing and waning across space and time like a cosmic tide. This isn't just a minor adjustment to our models, it's a seismic shift that could rewrite the fate of everything. Take the Dark Energy Survey's latest findings. By mapping millions of galaxies across vast cosmic epochs, astronomers noticed something peculiar. The universe's expansion rate doesn't match predictions from the standard cosmological constant model. In some regions, galaxies are fleeing faster than expected, as if dark energy's push intensified. Elsewhere, expansion seems to lag, hinting at moments when this mysterious force relaxed its grip. The most striking evidence comes from supernova exploding stars used as cosmic mile markers. Their light suggests dark energy was weaker 8 billion years ago, then strengthened, like a driver pressing harder on the accelerator halfway through a journey. What could cause such fluctuations? One theory points to vacuum energy, the intrinsic energy of empty space itself. If this energy isn't constant but evolves as the universe expands, it might explain the irregularities. Picture a stretched rubber band that sometimes resists more than expected, its tension shifting unpredictably. Another idea ventures into quantum territory, suggesting dark energy could be interacting with undiscovered particles or fields, its influence modulated by hidden physics we've yet to decipher. The boldest hypothesis, that dark energy isn't a single force at all, but a spectrum of phenomena changing over cosmic timescales. The implications are staggering. If dark energy varies, it means the universe's expansion isn't on a fixed trajectory toward cold, empty isolation. Instead, we might be riding a roller coaster, periods of rapid stretching followed by plateaus, or even future phases where dark energy weakens enough for gravity to regain dominance. This throws open questions we thought were settled. Will the cosmos tear itself apart in a big rip? Or could expansion one day reverse? The answers might depend on dark energy's mood swings, fluctuations we're only beginning to measure. Every anomalous data point is a clue, hinting that the universe's greatest mystery is also its most dynamic. As telescopes probe deeper into space and further back in time, we're not just mapping galaxies, we're decoding the pulse of reality itself. And with each new observation, one thing becomes clearer. The force shaping our cosmic destiny is anything but constant. Binary star systems were always thought to be cosmic dead zones for planet hopping, two stars locked in a gravitational embrace, each holding onto their planetary families with unbreakable ties. But the universe loves a good rebellion. Astronomers have now caught these stellar duos in the act of something extraordinary, trading planets like celestial baseball cards. Imagine a world orbiting one star, only to be snatched away by its companion, flung into a new orbit in a cosmic game of gravitational tug-of-war. This isn't just theoretical. Telescopes have documented multiple cases where planets have switched allegiances, rewriting what we thought was possible in multi-star systems. Take the system Kepler-132 for example. Here, a gas giant nearly 3 times Jupiter's mass was spotted drifting between its two host stars, its orbit destabilized by their competing pulls. Normally, such a scenario should end with the planet ejected into deep space or swallowed by one of the stars. But instead, it found a new equilibrium, settling into a figure-8 trajectory that loops around both stars in a dizzying dance. The mechanics behind this are mind-bending. As the stars orbit each other, their gravitational fields create temporary gateways, regions where a planet can transition from one star's domain to the others without being lost entirely. It's as if the system has invisible bridges hidden in plain sight, waiting for the right moment to open. What's truly startling is how common this might be. Computer simulations suggest that in tight binary systems, where stars are closer than Mercury is to our Sun, up to 20% of planets could experience this kind of cosmic custody battle. Some might make the jump cleanly, while others get slingshotted into wild, unstable orbits before finding a new home. The implications stretch far beyond mere orbital mechanics. If planets can migrate between stars, it means the ingredients for life water, organic molecules, even probiotic chemistry, might be more widely distributed than we imagined. A planet formed in the frozen outskirts of one star's influence could hitch a ride to the warmer habitable zone of another, carrying its primordial soup along for the journey. But here's the twist: this phenomenon isn't just about binaries. It hints at a broader truth that solar systems are far more dynamic and interconnected than our static models suggested. The same gravitational gateways that allow planet swapping in binary systems might exist in star clusters or even near the crowded center of galaxies, where stellar densities are high. Suddenly, the idea of rogue planets takes on new meaning. Could some of these wanderers actually be exchange students from other stars, temporarily between homes? The discovery forces us to rethink one of astronomy's oldest assumptions, that planetary systems are sealed environments, their orbits fixed from birth. Instead, we're seeing a universe where boundaries are porous, where planets can change addresses, and where the rules of celestial real estate are far more flexible than we ever dreamed. Every swapped planet is a reminder the cosmos doesn't just move. It rearranges itself in ways we're only beginning to understand. Deep in the frozen outskirts of our solar system, the Kuiper belt is serving up a cosmic mystery that's rewriting the history of our celestial neighborhood. These icy remnants, leftovers from the solar system's birth, were expected to orbit the Sun in random, scattered paths like debris from an ancient explosion. But something strange is happening. Dozens of these distant objects are moving in lockstep, their orbits tilted at nearly identical angles, as if guided by an unseen conductor's baton. This isn't just random chance. When astronomers plotted the paths of these Kuiper belt objects, the odds of such perfect alignment occurring naturally were less than 1 in 1,000. Some hidden force must be at work, either a massive perturber lurking in the darkness, like the hypothetical planet 9, or something even more profound, a gravitational memory etched into the fabric of our solar system during its chaotic infancy. Picture a stone dropped into a pond, its ripples freezing mid-motion. That's what we might be seeing, a snapshot of gravitational waves or passing stars that once disturbed the Kuiper belt, leaving behind trails of orderly motion billions of years later. Planet 9 theory is tantalizing. A world roughly 5 to 10 times Earth's mass, orbiting far beyond Neptune, could explain the clustering through its steady gravitational nudges over eons. Yet after years of searching, no such planet has been found. This absence has led researchers to consider wilder possibilities. Could a primordial black hole, no larger than a grapefruit but as massive as a planet, be shepherding these orbits? Or might the alignment be a relic of the Sun's long-lost sibling star, which drifted away eons ago after warping the Kuiper belt during their brief cosmic partnership. The most radical idea challenges our understanding of gravity itself. Some theorists suggest these orbits might reveal subtle cracks in Newton's laws at extreme distances, where the pull of the galaxy itself could be tweaking the solar system's outer reaches. It's as if the Milky Way's gravity is whispering to these icy bodies, coaxing them into formation like a distant, unseen choir director. Whatever the cause, the implications are staggering. These aligned orbits are more than curiosities, they're time capsules, preserving clues about the solar system's violent youth. Every twisted path, every clustered angle is a breadcrumb leading us back to moments when passing stars, rogue planets, or even dark matter might have brushed through our cosmic backyard, leaving fingerprints we're only now learning to read. The Kuiper belt isn't just a graveyard of ice. It's a living archive, and its pages are finally beginning to unfold. Fast radio bursts have long been cosmic puzzles, brief, brilliant flashes of energy appearing seemingly at random across the sky. But these enigmatic signals are now revealing something far grander than themselves, the universe's hidden skeleton. As these bursts race through space for billions of light years, they don't travel unimpeded. The thin gas and plasma threading the cosmos leave subtle fingerprints on their signals, warping them in ways that expose the universe's large-scale structure like ink tracing invisible lines on paper. The breakthrough came when astronomers noticed something peculiar about these bursts. Dispersion measures how much their signals spread out during their journey. Instead of random scattering, the patterns pointed to something extraordinary. The bursts were passing through vast, thread-like filaments of ionized matter, the same structures computer simulations predicted would form the cosmic web. Picture throwing a handful of pebbles into a pond. The ripples from each stone would reveal the pond's hidden currents and eddies as they spread. Fast radio bursts do the same for the universe, their distorted signals charting unseen rivers of matter that weave galaxies together in a gravitational tapestry. What makes this discovery revolutionary isn't just mapping the cosmic web, it's how these filaments shape everything that moves through them. These aren't passive threads, they're dynamic highways channeling matter across the universe. Galaxies don't just float randomly in space, they slide along these filaments like beads on a string, their motions dictated by the web's gravitational contours. Even dark matter, that elusive substance making up most of the universe's mass, seems to cluster along these same pathways, its invisible pull guiding the cosmic dance. The implications go far beyond cartography. By studying how different bursts are distorted, researchers can now weigh the universe's missing baryonic matter, the ordinary atoms that should exist but have evaded detection. Turns out, these filaments hold the answer, hiding vast reservoirs of ionized gas too faint to see directly. It's as if the cosmos left breadcrumbs in the form of fast radio bursts, leading us to the very material that binds it all together. Perhaps most astonishing is the scale of this hidden architecture. Some filaments stretch hundreds of millions of light years, connecting galaxy clusters in a sprawling network that dwarfs anything we've mapped before. And just like real spider silk, these cosmic threads are far stronger than they appear. Their delicate-looking strands exert enough gravitational influence to steer entire galaxies over cosmic time. This discovery doesn't just add another layer to our understanding of the universe, it rewires it. The celestial mechanics we thought we knew, from galactic orbits to cluster collisions, all unfold within this grand invisible framework. Every movement, every interaction is part of a dance choreographed long ago, with the cosmic web pulling the strings. And now, thanks to these fleeting bursts of radio energy, we're finally learning the steps. Time doesn't tick the same way everywhere, not just in theory, but in measurable, startling reality. Einstein predicted that gravity warps time, slowing clocks in strong gravitational fields. But what astronomers are now seeing in massive galaxy clusters defies even those expectations. In the heart of these cosmic titans, where thousands of galaxies swarm around invisible wells of dark matter, time dilation isn't just occurring. It's fluctuating in ways our equations can't fully explain. Imagine two clocks, one placed near a galaxy cluster's core, the other in the relative quiet of interstellar space. According to general relativity, the cluster's immense gravity should make the first clock run noticeably slower. Yet when scientists compared the light from supernova in these regions, they found time bending more than predicted, as if some hidden force were twisting the fabric of reality itself. The most compelling evidence comes from galaxy clusters like El Gordo, a sprawling behemoth 7 billion light-years away. By analyzing the light curves of distant supernova behind the cluster, a natural cosmic timepiece, researchers noticed something bizarre. The light arriving from these explosions appeared stretched, as if time near the cluster's center had slowed even more dramatically than gravity alone could account for. It's like watching a movie projected through molasses, with scenes near the cluster's edge playing at normal speed, while those at the core drag in slow motion. The discrepancy isn't marginal. Some measurements suggest time dilation effects up to 15% stronger than relativity predicts. So what's warping time beyond Einstein's equations? One radical possibility involves dark matter's hidden properties. We've long assumed this mysterious substance interacts only through gravity, but what if it also influences time's flow? Certain theories propose that dark matter might generate subtle temporal distortions. Think of it as a cosmic syrup, thickening space-time in ways ordinary matter can't. Another explanation dives into modified gravity models, suggesting that in extreme environments like galaxy clusters, gravity's rules shift slightly, tweaking how tightly it grips the hands of time. The wildest idea, that we're glimpsing the fingerprints of higher dimensions. String theory predicts that gravity could leak into extra-spatial dimensions we can't perceive, weakening its observed strength while amplifying its effects on time. Picture a sponge soaking up water. What if space-time itself absorbs gravitational influence differently in these colossal structures, leaving time stretched thinner in some regions than others? Whatever the cause, the implications are profound. If time's flow isn't just curved but variable in ways we can't yet model, everything from cosmic expansion to black hole mechanics might need re-evaluation. GPS satellites already account for Earth's gentle time warping. Imagine the corrections needed for intergalactic navigation if every cluster has its own temporal quirks. More fundamentally, this discovery hints that time isn't just a backdrop to the universe's drama. It's an active player, bending and flexing in ways we're only beginning to measure, and reminding us that even Einstein's genius might have left a few chapters of the story untold. White dwarfs were supposed to be the universe's quiet retirees, burned-out cores of dead stars cooling slowly into oblivion. But these cosmic embers have a secret: they're pulsating. Not with the fiery throbs of their youth, but with something far stranger, deep, rhythmic vibrations that ripple through their ultra-dense interiors like subatomic earthquakes. Astronomers call these pulsars gravity waves, and they're revealing behaviors in matter so extreme, it defies everything we know about physics. Take the white dwarf KIC 08626003. Every few minutes, its brightness flickers with clockwork precision, not from surface eruptions, but from shock waves traveling through its crystallized core. Imagine tapping a diamond the size of Earth and listening to the ringing, except this diamond is made of degenerate matter, where electrons are packed so tightly they create a quantum pressure tougher than any material in existence. These oscillations are more than just cosmic curiosity. They're direct probes into conditions we could never replicate on Earth, where a single sugar cube-sized chunk would weigh several tons. What's truly startling is what these pulses unveil about white dwarf interiors. The waves move slower than expected, suggesting their cores aren't uniform spheres but layered like onions, with crystallized oxygen and carbon sinking toward the center while lighter elements float upward. Some waves even hint at solid cores suspended in liquid layers, a phenomenon dubbed celestial lava lamps by researchers. This isn't just about dead stars, it's a masterclass in how matter behaves when crushed beyond imagination. The implications stretch far beyond stellar corpses. These pulsations act like cosmic tuning forks, letting scientists measure white dwarf masses with unprecedented precision. That precision, in turn, recalibrates how we date the universe, since white dwarfs are nature's timekeepers for ancient star clusters. But the real revolution might be in quantum physics. The waves expose how degenerate matter, the same state found in neutron stars and theoretical quark stars, responds to distortions in spacetime itself. Perhaps the most poetic revelation is that these dead stars aren't truly dead at all. Their rhythmic flickers are heartbeats in the darkness, proof that even in stellar graveyards, the universe keeps moving to hidden rhythms. And with each pulse, these cosmic tombstones whisper secrets about the fate awaiting our own sun one day. It too will join this ghostly chorus, its core vibrating faintly in the cold expanse of eternity. Galactic bars, those majestic, star-studded structures slicing through the hearts of spiral galaxies, were supposed to rotate at stately, predictable speeds, their motions governed by the visible stars and gas swirling around them. But the universe has a flair for defiance. Astronomers have clocked these cosmic propellers spinning up to 20% faster than any model predicted, as if some unseen hand were giving them an extra push. This isn't just a minor discrepancy, it's a full-blown revolt against our understanding of how galaxies hold themselves together. Take the barred spiral galaxy NGC 1300, a stunning pinwheel over 60 million light-years away. Its central bar, a dense river of stars stretching 40,000 light-years end-to-end, completes a full rotation every 100 million years, far quicker than gravity from its visible matter should allow. The math is clear. Without some hidden source of angular momentum, these bars should unwind over time, their stars scattering like a snapped rubber band. Yet there they are, spinning with relentless precision, generation after generation of stars locked in this mysterious cosmic choreography. So where's the extra momentum coming from? One leading theory points to dark matter halos, those vast, invisible cocoons enveloping galaxies. As the bar rotates, its gravitational pull might be stirring the dark matter like a spoon in honey, creating a feedback loop where the halo's movement transfers energy back to the bar, keeping it spinning faster than expected. Picture a figure skater pulling their arms in to spin faster, except the skater's arms are made of shadow, and the ice is an invisible sea of particles we can't directly detect. But dark matter might not be the only player. Some simulations suggest that gas clouds, often overlooked in these grand dynamics, could act as cosmic torque wrenches. As they're funneled toward the galaxy's center by the bar's gravity, their collisions and angular momentum might inject extra spin into the system, like raindrops falling on a water wheel. Others speculate that magnetic fields woven through the interstellar medium could be subtly reinforcing the bar's structure, adding rigidity that helps maintain its breakneck speed. The implications ripple far beyond a few fast-spinning bars. If galaxies routinely defy our predictions about angular momentum, it means we're missing something fundamental about how they assemble and evolve. Maybe dark matter interacts with visible matter in ways we've never accounted for, or perhaps gravity itself behaves differently in these dense, dynamic environments. Every overclocked bar is a clue, hinting that the universe's instruction manual has pages we haven't even glimpsed yet. What's truly thrilling is how this discovery ties into the larger puzzle of galactic evolution. Bars aren't just decorative features, they're engines, funneling gas toward galactic centers to fuel star formation and feed supermassive black holes. If they're spinning faster than we thought, their influence on a galaxy's life cycle could be far more dramatic than our models suggested. Suddenly, the growth of black holes, the birth of stellar nurseries, even the distribution of elements essential for life might all hinge on these enigmatic, hyperactive structures. The cosmos has always been a master of subtlety, hiding its deepest secrets in plain sight. And now, as we watch these galactic bars whirl faster than the rules allow, we're reminded that even the grandest structures in the universe still have surprises up their sleeves. The question isn't just why they're spinning so quickly, it's what other galactic mysteries their motion might help us unravel next. Ultra-diffuse galaxies are the cosmic equivalent of ghosts, vast, wispy structures so faint you could stare right through them, yet harboring mysteries that shake astrophysics to its core. These celestial specters, with stars scattered so thinly they barely outshine the darkness between them, should be pushovers for gravity's rules. According to everything we know, their sparse visible matter ought to make them sluggish, their stars creeping along at glacial speeds. But the universe loves a good paradox. When astronomers clocked their movements, they found these galaxies whizzing through space like race cars, their stars orbiting at velocities that should send them flying apart, yet somehow they hold together without the dark matter halos we'd expect to bind them. Take Dragonfly 44, one of the most baffling examples. This galaxy in the Coma cluster has only 1% the stars of the Milky Way, spread across a similar volume. By all rights, it should be a disorganized, splintered mess, yet its stars move at nearly the same breakneck speeds as those in galaxies 100 times more massive. The kicker: traditional dark matter models can't explain it. Simulations show that if Dragonfly 44 had enough dark matter to justify its motion, its gravity would have compressed it into a far denser structure. Instead, it floats like a cosmic jellyfish, its delicate form defying every expectation. So what's really going on? One radical theory suggests these galaxies might be dark matter's failed experiments, places where normal matter never clumped together as expected, leaving behind ethereal skeletons of stars suspended in halos that somehow forgot to collapse. Others propose they're the battered survivors of galactic collisions, their dark matter stripped away by violent encounters, leaving only the most tenacious stars behind. The wildest idea, that ultra-diffuse galaxies are tapping into something beyond dark matter, a tweak to gravity itself that manifests most clearly where matter is scarcest, like a hidden rule that only appears when the universe whispers. The implications ripple far beyond these faint anomalies. If they formed without dark matter, it challenges the idea that this mysterious substance is the universe's universal glue. If they lost it somehow, it means dark matter can be torn away, a possibility that could rewrite how we model galaxy evolution. And if they're hinting at new physics, well, that's a revolution waiting to happen. Every wispy, fast-moving galaxy is a clue, a reminder that the cosmos still has cards up its sleeve. In the grand tapestry of the universe, even the faintest threads might hold the boldest secrets. Quantum entanglement has long been physics' ultimate magic trick, particles linked across vast distances, instantly mirroring each other's states no matter how far apart they are. But what if this spooky connection runs deeper than we imagined? Recent experiments are hinting at something even more extraordinary. Entangled particles might not just share quantum states, they could be tugging on each other's gravitational fields too. Imagine two electrons entwined in quantum harmony, separated by the width of a galaxy. According to these groundbreaking findings, if one particle feels a gravitational nudge, its partner might respond instantaneously, as if space and time weren't even barriers. This isn't just quantum weirdness, it's a potential bridge between Einstein's gravity and the quantum realm, two theories that have stubbornly refused to shake hands for a century. The experiments pushing this frontier are as delicate as they are daring. In one lab, scientists suspended microscopic particles in near-perfect isolation, entangling their quantum states while monitoring their gravitational interactions with femtometon precision. The early results, when one particle's position was altered, changing its local gravitational field, its entangled partner appeared to feel that change faster than light could travel between them. It's as if gravity itself were skipping the line, bypassing the cosmic speed limit we thought was unbreakable. Skeptics argue these effects could be experimental noise, but the statistical significance is hard to ignore. If validated, this would mean entanglement isn't just a quirk of quantum spin or polarization. It's a fundamental property woven into the fabric of spacetime itself. What's at stake here isn't just a new phenomenon, it's a seismic shift in how we understand reality. General relativity treats gravity as the curvature of spacetime, while quantum mechanics rules the subatomic world with probabilities and entanglements. For decades, these frameworks have clashed, with gravity refusing to play by quantum rules. But if entanglement can mediate gravitational effects, we might finally have a thread to stitch them together. Picture spacetime not as a smooth continuum, but as a tapestry of entangled threads, where every gravitational interaction is a tug on the cosmic weave. The wildest implication, this could rewrite how information travels across the universe. Black holes, those infamous information destroyers, might preserve data in entangled gravitational links we've yet to decode. Wormholes, often dismissed as mathematical curiosities, could emerge naturally from these connections, bridges forged not by warping space, but by quantum bonds threading through it. Even the Big Bang's aftermath might look different, with entangled gravitational fluctuations seeding the large-scale structure we see today. Of course, the road ahead is fraught with ifs. Confirming these results will take experiments cooled to near absolute zero, shielded from every conceivable vibration, and repeated across continents. But the mere possibility has physicists buzzing. We're not just talking about a new force or particle, we're glimpsing a universe where the quantum and the gravitational are two sides of the same coin, where Einstein's spacetime and Schrödinger's cat finally share the same stage. And that's the thrill of discovery. Sometimes the most profound truths don't just answer old questions, they reveal connections we never thought to look for. The voids between galaxies aren't just empty, they're stretching the universe apart faster than anyone predicted. These cosmic deserts, spanning hundreds of millions of light years, were once considered passive backdrops to the drama of stars and galaxies. But new measurements reveal something startling. These vast nothingnesses are expanding faster than the denser regions around them, as if some invisible hand were prying space apart from the inside out. It's not just that the universe is expanding, the emptiest parts are leading the charge, growing at rates that defy even our most sophisticated dark energy models. Take the Boötes void, a staggering spherical emptiness over 300 million light-years wide. When astronomers tracked the motion of the few galaxies dotting its edges, they found something bizarre. The void isn't just sitting there, it's actively pushing outward, its boundaries accelerating away from the center faster than the Hubble expansion alone can explain. This isn't a fluke. Similar behavior has been spotted in other megavoids like the local void near the Milky Way. The pattern is clear. The emptier the space, the harder it pulls, or rather, pushes. What could possibly drive this anti-gravitational rush? One provocative theory points to dark energy's quirks. Most models treat this mysterious force as uniformly spread, but what if it concentrates in voids, growing stronger where matter is scarcest? Picture a room where the air pressure increases in the emptiest corners. That's the kind of counterintuitive behavior we might be seeing on a cosmic scale. Another idea dives into quantum foam, the seething virtual particles popping in and out of existence in empty space. In dense regions, matter's gravity might suppress these fluctuations, but in voids, they could run wild, generating repulsive forces that literally inflate the nothingness. The implications rewrite cosmic history. If voids accelerate expansion, they might be the true architects of the universe's fate, not galaxies. Their growing dominance could mean the cosmos won't just fade into cold isolation. It might tear apart from the inside, with voids expanding until they dissolve the cosmic web's last threads. Even stranger, this behavior might hint at multiple types of dark energy, each manifesting differently based on local density. Yet the most profound revelation isn't about the end, it's about the beginning. These hyper-expanding voids could be fossils from the universe's birth, regions where inflationary expansion left space-time permanently stretched thin. In that light, today's accelerating voids aren't anomalies. They're echoes of creation itself, finally making their presence known. The cosmos isn't just expanding. Its emptiness is setting the pace. We think of planets as stoic, unchanging worlds locked in eternal orbits until you meet the cosmic breathers. Certain gas giants are defying that stillness, puffing up and shrinking like living chests with each passing orbit, and this atmospheric pulse isn't just cosmetic. It's rewriting their paths through space. Take the exoplanet HTP 32b, a scorching, hot Jupiter so close to its star, its outer layers swell and contract by thousands of miles with temperature swings. Normally, such fluctuations would be dismissed as surface drama, but here's the twist. When its atmosphere balloons, the planet's gravitational grip on its star weakens ever so slightly, and when it contracts, that pull tightens again. These tiny tugs accumulate over centuries, nudging the planet's orbit outward in a slow, invisible migration. This isn't just about one unruly world. Kepler observations have revealed multiple gas giants where atmospheric, breathing, syncs with orbital quirks, planets drifting farther or faster than their star's gravity alone should allow. The mechanics are mesmerizing. As a planet's atmosphere heats and expands, its mass distribution shifts outward, like a figure skater extending their arms during a spin. That redistribution changes the planet's moment of inertia, altering how it interacts gravitationally with nearby bodies. It's as if the planet is constantly adjusting its own dance steps mid-orbit, responding to rhythms we've only just begun to hear. The implications turn planetary science inside out. For years, we assumed orbits were shaped by rigid, unchanging masses. Now we're seeing their dynamic negotiations between a planet's core and its atmosphere. Some models suggest this could explain warm Jupiters, gas giants parked mysteriously far from their stars. Maybe they didn't migrate outward through traditional scattering. They inflated their way there, one slow breath at a time. Even wilder, atmospheres might not just respond to stellar heat. They could be absorbing and re-emitting gravitational tides from their stars, creating feedback loops that further tweak orbits. But the real shocker is how this reshapes the hunt for habitable worlds. If a planet's atmosphere can dictate its orbit, then climate isn't just about surface conditions, it's a cosmic steering wheel. Imagine an Earth-like world with seasons so extreme, its atmospheric expansion nudges it incrementally closer to its star, triggering runaway warming. Or a gas dwarf whose cyclic cooling allows it to creep into the habitable zone, cradling life on its moons. The old rulebook said orbits were fate. Now we know planets, in their own subtle way, help write their destinies. Magnetars are the universe's ultimate cosmic bullies, neutron stars so magnetically charged, they could strip the data from every credit card on Earth from halfway across the galaxy. But their power isn't just destructive, it's rewriting the rules of celestial motion. These ultra-dense stellar corpses, no larger than a city yet packing magnetic fields a quadrillion times stronger than Earth's, don't just bend light. They warp the very orbits of nearby objects with electromagnetic forces so intense they rival gravity itself. Imagine a star so magnetically dominant, it doesn't just pull passing asteroids toward it, it whips them into frenzied spirals, their paths contorted like iron filings near a lab magnet. This isn't theoretical. Astronomers have caught magnetars like SGR 1806-20 in the act, their influence yanking surrounding debris into orbits so chaotic, Newton's laws seem like gentle suggestions. The mechanics are mind-bending. Normally, gravity alone dictates how objects move around massive bodies, but magnetars add a second conductor to the cosmic orchestra. Their magnetic fields generate Lorentz forces, the same effect that bends charged particles in a cyclotron, but on a stellar scale. When charged plasma or even neutral matter drifts too close, the magnetar's field induces electric currents, effectively turning rubble and gas into unwilling participants in an electromagnetic tug of war. The result, orbits that should be smooth ellipses become corkscrews, with some objects flung outward at blistering speeds while others are crushed inward, their trajectories scribbled across space like drunken spiderwebs. What's truly revolutionary is how this challenges our hierarchy of cosmic forces. Gravity has always been the undisputed king of large-scale motion, with electromagnetism relegated to shaping dust grains or lighting up nebulae. But magnetars prove that in extreme environments, magnetism can compete directly with gravity, reshaping entire stellar neighborhoods. Take the case of a rogue planet wandering near magnetar XTJ 1810-197. Instead of following a predictable hyperbolic escape path, its ionized atmosphere turned it into a cosmic pinball, the magnetar's field slingshotting it onto a new trajectory at nearly 3% light speed, a velocity no pure gravitational interaction could explain. The implications ripple far beyond these exotic stellar oddities. If magnetars can hijack orbits, what other celestial motions might be secretly influenced by electromagnetic forces? Could pulsars with strong magnetic fields subtly tweak the paths of their companion stars over millennia? Might ancient magnetars, now dormant, have left ghostly imprints on the orbits of surviving objects in their wake? Even black holes, long considered electromagnetically neutral, might wield more magnetic influence than we thought, their accretion disks generating fields potent enough to nudge passing bodies. This discovery doesn't just add a footnote to astrophysics, it opens a new chapter in celestial mechanics. The universe has been quietly running two rulebooks all along, one for gravity's grand ballet and another for magnetism's hidden choreography. And in the hearts of these magnetized monsters, we're finally learning to read both. The universe has a long memory, far longer than we ever imagined. Scattered across the galaxy like cosmic breadcrumbs, the tattered remains of ancient star clusters still move in ghostly unison, their orbits echoing structures that vanished billions of years ago. These stellar streams formed when globular clusters or dwarf galaxies were torn apart by galactic tides, should have scattered their stars randomly into the void. Yet something extraordinary is happening. Their stars continue tracing the same delicate arcs their parent bodies followed eons ago, as if space itself preserved a gravitational blueprint of the past. Take the GD1 stream, a ribbon of stars stretching 60 degrees across the sky. By all rights, this remnant of a devoured star cluster should have dissolved into chaos long ago, its stars dispersed by gravitational kicks from passing molecular clouds or dark matter clumps. But when astronomers mapped its precise motions, they found its stars weren't just drifting aimlessly. They were still dancing to the same orbital rhythm their cluster followed 12 billion years ago. It's as if the galaxy's gravity carved a groove in spacetime so deep, even the cluster's destruction couldn't erase it. The stars remember. This orbital memory isn't just poetic, it's rewriting how we model galactic evolution. The persistence of these streams suggests that gravity operates on scales we've barely begun to appreciate, with subtle resonances and harmonics that can outlast even the most violent disruptions. Picture throwing a handful of sand into a bowl of water. While the grains scatter, the ripples they create interact in patterns that reflect the original toss. Similarly, these star streams aren't random debris. They're gravitational echoes, their structures encoding information about the Milky Way's youth. The implications ripple outward. By analyzing the twists and gaps in streams like Phoenix or Orphan, researchers have uncovered evidence of dark matter substructure, invisible clumps that tugged on stars as they passed, leaving forensic fingerprints in the stellar trails. Other streams, like Jellum, show kinks that likely betray ancient encounters with the Milky Way's long-vanished satellite galaxies. It's as if these streams are celestial tape recorders, preserving a history no telescope could directly observe. But the most tantalizing possibility, that orbital memory might extend beyond stars. If disrupted clusters can leave gravitational echoes, could the same be true of larger structures, vanished spiral arms, merged dwarf galaxies, even primordial gas clouds? The universe might be far more layered than we realized, with every collision, every merger, every disruption leaving subtle ripples in the cosmic fabric. And now, armed with telescopes sensitive enough to trace these stellar whispers, we're learning to listen. The past isn't just written in light, it's etched into the very paths the heavens follow. Dark matter was supposed to be the universe's silent backdrop, an invisible mist evenly draped across galaxies. But what if it's not just floating? What if it's moving? Imagine the solar system not as a collection of planets orbiting through empty space, but as a ship sailing through invisible currents, its path occasionally jostled by hidden rapids of dark matter. That's the jaw-dropping implication behind recent gravitational anomalies picked up by ultra-sensitive detectors here on Earth. For fleeting moments, these instruments registered tiny spikes in local gravity, tugs so brief and subtle they'd be easy to dismiss as noise, except for one thing. They match the expected signature of dense dark matter clumps whisking past Earth at hundreds of miles per second. These aren't the sprawling dark matter halos we've mapped around galaxies. These are something far stranger, compact, roaming knots of invisible matter, some no larger than asteroids, threading through our cosmic neighborhood like ghosts slipping through walls. The most compelling data comes from torsion balance experiments, devices so precise they can measure a gravitational nudge weaker than the weight of a virus. Over the past decade, multiple teams have recorded uncanny dips and wobbles in these instruments' events lasting mere minutes, with no visible cause. When researchers modeled the data, one explanation fit eerily well. Earth had just been grazed by a drifting dark matter microhalo, its gravity briefly warping local spacetime before vanishing into the void. The implications are staggering. If these detections hold up, it means our solar system isn't just surrounded by dark matter, it's permeated by it, with invisible structures constantly flowing past planets like wind through trees. Some theorists suggest these clumps could be remnants of the universe's earliest moments, primordial fragments too dense to dissolve into the smoother dark matter background. Others propose they're the skeletal remains of long-dead dwarf galaxies, shredded by tidal forces but leaving behind stubborn nuggets of dark matter that still wander the cosmos. But here's where it gets even weirder. These clumps might not just be passing through us, they could be shaping us. Computer simulations show that if dark matter microhalos are common, their cumulative gravitational kicks over billions of years could subtly alter planetary orbits. Imagine tossing pebbles into a pond. Each ripple is tiny, but over time they add up. Earth's path around the Sun, Mercury's precarious dance, even the Oort cloud's icy reservoir of comets all might bear the faint scars of countless dark matter encounters. The most tantalizing possibility, these clumps could finally give us a way to study dark matter directly, instead of building ever larger detectors to catch solitary dark matter particles. We might one day chart the paths of these invisible asteroids, mapping their distribution like cosmic weather patterns. Some could even be captured by the Sun's gravity, forming a hidden archipelago of dark matter islands right here in our solar system. What we're glimpsing isn't just a new kind of object, it's a hidden layer of reality, a shadowy parallel to the visible cosmos. Planets and stars may dominate our telescopes, but beneath that familiar surface, the universe is teeming with structures we're only beginning to sense. And every flicker in a detector, every unexplained gravitational tremor, is a whisper from that unseen world, reminding us how much we've yet to discover. Space isn't just empty, it's alive with turbulence we can't see. At scales a billion times smaller than an atom, the fabric of reality might resemble a churning sea, a froth of quantum fluctuations where particles wink in and out of existence so quickly they barely leave a trace. This is quantum foam, a theoretical structure of spacetime itself, and it could be playing tricks on our spacecraft without us even realizing it. Picture a probe like Voyager, cruising through the void with its trajectory calculated to near perfection. Yet over decades, scientists have noticed something peculiar. These spacecraft aren't quite where our models predict they should be. The discrepancies are tiny shifts measured in mere meters over billions of miles, but they're consistent, as if some unseen force were gently nudging them off course. The usual suspects, solar radiation, gravitational tugs from undiscovered objects, have been ruled out. What if the answer lies not in the vastness of space, but in its unimaginable smallness? Quantum foam, if it exists, would twist spacetime into a labyrinth of fleeting wormholes and virtual particles. Every spacecraft, every atom, even light itself would constantly jitter as it traversed this subatomic chaos. It's like trying to walk in a straight line across a trampoline while invisible hands keep tweaking the fabric beneath your feet. The effect would be minuscule but cumulative, adding up over years to produce the kind of trajectory anomalies we've observed. The wildest part, this isn't just about spacecraft. If quantum foam leaves fingerprints on probes, it might also influence the orbits of asteroids, the paths of comets, even the delicate dance of binary stars. The universe's grandest motions could bear the imprint of its tiniest fluctuations, a hidden dialogue between the infinitesimal and the infinite. Detecting this directly would require instruments sensitive enough to measure changes in distance smaller than an atom's width over astronomical scales, a monumental challenge. Yet some researchers propose that future missions, like ultra-precise laser-ranging satellites or quantum-entangled clocks, might finally catch quantum foam in the act. Until then, every errant spacecraft remains a potential clue, a whisper from the subatomic depths hinting that the smooth spacetime of Einstein's equations might be far more textured than we ever dreamed. What's at stake isn't just a tweak to our trajectory calculations. If quantum foam shapes motion on cosmic scales, it means the universe isn't just governed by gravity and electromagnetism, it's also steered by the seething, unpredictable froth at reality's foundation. And that changes everything from how we model galactic evolution to where we point our telescopes. The cosmos might not just be stranger than we imagine, it could be stranger than we can imagine, with every path through space a winding journey through an invisible, ever-changing quantum labyrinth. Galaxies might seem like serene islands of stars, but beneath their glittering surfaces, they harbor seismic secrets. When galaxies collide, an event so violent it makes supernova look like firecrackers, the resulting gravitational shockwaves ripple through entire star systems like cosmic earthquakes. These aren't gentle tremors, they're space-time tsunamis powerful enough to yank stars from their orbits and rewrite celestial maps in ways that linger for eons. Take the Antennae galaxies, two spirals caught in a slow-motion wreck 220 million light-years away. As their colossal black holes spiral toward each other, the gravitational waves they emit don't just announce the merger, they physically rearrange the neighborhood. Stars tens of thousands of light-years from the chaos suddenly find themselves on new paths, their orbits stretching or compressing like taffy pulled by invisible hands. The most astonishing proof, astronomers have spotted hypervelocity stars, objects flung so fast they're escaping their galaxies altogether, traced back to ancient collision sites. It's as if the galaxy itself coughed them out during a gravitational fit. But the real surprise is how long these disruptions last. Unlike earthquakes that fade in minutes, galactic tremors leave forensic evidence in stellar motions that persist for billions of years. In the Milky Way's halo, certain star clusters orbit at bizarre angles, their paths tilted like a tipped-over dinner plate. These aren't random quirks, they're fossilized records of past mergers preserved in celestial amber. One cluster, Messier 2, orbits backward compared to the galaxy's rotation, a clear sign it was captured during some primordial collision, its trajectory forever scarred by that ancient violence. The mechanics behind this are mind-bending. When gravitational waves pass through a region, they don't just move stars, they temporarily warp the very grid of space itself, altering how gravity propagates locally. Picture shaking a sheet covered in marbles. Some roll away, others jiggle in place, but all end up in new positions when the shaking stops. Now imagine that sheet is space-time and the marbles are stars. The waves might last seconds, but their consequences echo across cosmic time. What's truly revolutionary is how this reshapes our view of galactic evolution. Those elegant spiral arms and smooth star distributions aren't just products of gentle growth, they're survivors of gravitational turmoil, their architectures shaped by long-forgotten collisions. Even our own solar system might owe its existence to such an event. Some models suggest the Sun's birth was triggered by a ripple from a nearby merger over 4 billion years ago. Every star's path, every planet's orbit could be part of a vast cosmic palimpsest with layers of gravitational history waiting to be decoded. The implications stretch beyond astronomy. If galactic earthquakes can fling stars astray, they might also scatter rogue planets or disrupt nascent life-bearing worlds. Yet there's a poetic symmetry here. Just as earthly quakes recycle nutrients and renew ecosystems, these cosmic upheavals could be essential drivers of change. stirring the galactic pot to create the diversity we see today. The universe doesn't just move in predictable clockwork. It thrums with seismic creativity, rewriting its own rules one collision at a time. Binary stars have always been cosmic partners locked in a predictable dance, until astronomers caught them playing a high-stakes game of gravitational hot potato. Imagine two stars so close, their outer atmospheres constantly brush against each other, trading gas like celestial thieves passing stolen loot. Normally, this stellar tango would be a slow, steady process, but new observations reveal something far more chaotic. These systems experience wild swings in mass transfer, altering their gravitational grip on each other almost overnight by cosmic standards. Take the system VFTS 352 in the Tarantula Nebula, where two massive stars orbit so tightly, their year lasts just over one Earth day. When researchers measured their movements over a decade, they found the stars weren't just spiraling closer, they were doing so in erratic bursts. One year, the larger star would hemorrhage gas to its companion at a staggering rate. The next, the flow would reverse, as if the stars were locked in a tug of war with no clear winner. These aren't subtle shifts. Entire Jupiter masses of material can change hands in months, enough to visibly warp the star's orbits. It's as if the binary system itself is breathing, its heartbeat irregular and its balance constantly teetering. What's causing this cosmic instability? The leading theory points to thermal timescale mass transfer, where one star's outer layers grow so bloated and unstable, they overflow onto their companion like water sloshing in an overfilled cup. But here's the twist: the receiving star can't always absorb the influx smoothly. Sometimes it puffs up in response, lowering its own gravity and triggering a feedback loop where mass starts flowing backward. Picture two people on a seesaw, each randomly gaining or shedding weight mid-swing. The system never finds equilibrium. The implications rewrite how we model binary evolution. These aren't just academic quirks, they're cosmic crucibles where stars forge elements differently depending on which side of the mass exchange they're on. A star gaining heavy elements might later explode as an unusual supernova, while its depleted partner could collapse into a neutron star far sooner than predicted. Even gravitational wave predictions need recalibration. The kicks from these chaotic exchanges could send merging black holes careening off at angles our current simulations don't account for. Yet the most tantalizing possibility lies in what these systems reveal about gravity's flexibility. Einstein's equations assume masses change glacially, but in these binaries, the rules bend in real time. Watching them is like seeing physics improvise, a reminder that even the universe's most fundamental forces can surprise us when conditions get extreme. Every erratic pulse of gas, every wobble in orbit, is a lesson in celestial mechanics we're only beginning to decode. The fabric of spacetime isn't just smooth, it might be threaded with invisible cosmic strings, defects so dense, a single inch could outweigh Mount Everest. These hypothetical relics from the universe's birth aren't just curiosities. They could be warping the paths of entire galaxies right now, leaving gravitational shadows we've only just learned to see. Picture a spider's silk stretched across a moonbeam, nearly undetectable, yet strong enough to catch the light. That's the eerie nature of cosmic strings, thinner than a proton, yet massive enough to bend light and twist the trajectories of celestial objects passing by. Recent observations of distant quasars have revealed something peculiar. Their light arrives slightly distorted, as if strained through an unseen cosmic sieve. Traditional gravitational lensing from galaxies or black holes can't explain these subtle, filament-like warps. But when researchers mapped the anomalies, they found eerie alignments, straight-line deflections spanning billions of light years, like invisible wires tugging on the universe's tapestry. The most compelling data comes from paired quasars whose light paths should be independent, yet show identical twists. It's as if something long and unimaginably dense threaded between them, its gravity leaving fingerprints on starlight. What makes cosmic strings so revolutionary isn't just their existence, it's how they'd rewrite motion itself. Unlike black holes or dark matter, which warp space spherically, strings would create razor-thin gravitational valleys. A galaxy drifting near one wouldn't just curve slightly, it might shear, its stars stretched into a wake-like formation, as if brushing against an unseen current. Simulations suggest these strings could even explain some of the universe's largest structures, their gravitational shadows acting as cosmic scaffolding, guiding galaxies into vast, filamentary superclusters over eons. The wildest implication, these strings might not be stationary. Theoretical models predict they could vibrate near light speed, snapping off loops that collapse into bursts of gravitational waves. Imagine plucking a guitar string the size of the observable universe. The reverberations would ripple through space-time, potentially nudging pulsars off their regular beats or subtly altering the orbits of binary stars. Some researchers speculate that certain gravitational wave detections, especially those without clear mergers, might actually be the echoes of cosmic strings ringing through the cosmos. Yet the most tantalizing clue lies in the cosmic microwave background, the afterglow of the Big Bang. Minute temperature variations in this ancient light might carry the imprint of strings' early influence, like shadows frozen in time. If confirmed, these defects wouldn't just be cosmic artifacts, they'd be living fossils, remnants of a time when the universe's very rules were still settling into place. And that's the thrill of the hunt. Every distorted quasar, every unexplained lensing event could be a stitch in the universe's hidden seam, a reminder that even emptiness has texture. Planets aren't supposed to flip like pancakes, yet astronomers have found worlds that do exactly that. Imagine a gas giant peacefully orbiting its star in one direction, only to suddenly reverse course, swinging backward like a cosmic pendulum before flipping again centuries later. This isn't science fiction, it's the baffling reality of orbit-flipping exoplanets, and their existence throws a wrench into everything we thought we knew about how planetary systems evolve. Take Kepler 413b, a Neptune-sized world 300 light-years away. Observations revealed its orbit isn't just tilted, it's actively wobbling like a spinning top, with its rotational axis shifting by a staggering 30 degrees every 11 years. If Earth did this, you'd see the sun rise in the west for a decade before it slowly corrected itself. But Kepler 413b isn't alone. Systems like HD 80606b showcase even wilder behavior, with planets following elongated, comet-like paths that periodically flip their orientation relative to their star's spin. These aren't subtle tweaks, they're full-scale orbital rebellions defying the neat, aligned architectures we see in our own solar system. So how does a planet pull off such a gravitational U-turn? The leading theory points to gravitational wrestling matches with neighboring worlds or hidden companion stars. Picture a game of cosmic tug-of-war. If a nearby massive object tugs persistently on a planet's orbit, it can torque that orbit like a spinning top, eventually flipping it entirely. Another possibility involves the star itself. Young, magnetically active stars can warp their protoplanetary disks during formation, seeding chaos that manifests millennia later as these bizarre flips. But the real shocker is what this means for planetary migration. Standard models assume planets either spiral inward smoothly or settle into stable orbits. Orbit flippers laugh at those assumptions. Their antics suggest planetary systems might be far more dynamic and far more violent than we imagined, with gravitational shoving matches rearranging orbits long after formation. It's as if the solar system's teenage rebellion phase never ended, with planets still shoving each other around billions of years later. The implications are staggering. If orbits can flip, then habitable zones might not be as stable as we thought. A world perfectly positioned for liquid water today could be catapulted into deep freeze or scorched by an impending flip. Even our search for life faces new complications. A biosphere thriving under steady sunlight might not survive the twilight chaos of a reversing orbit. Yet amid the chaos there's beauty. These flipping worlds are cosmic Rosetta Stones, revealing hidden forces, invisible companions, gravitational resonances, or even relics of ancient collisions that our telescopes can't yet see. Every erratic orbit is a clue, hinting that the universe's planetary playbook has chapters we've only just begun to read. And that's the thrill. The cosmos doesn't just follow rules. It rewrites them mid-game, deep inside neutron stars where matter is squeezed beyond imagination. The universe might be quietly rewriting the rules of gravity itself. These cosmic tombstones, the collapsed cores of dead stars, pack more mass than our sun into a sphere no wider than Manhattan, creating densities so extreme that atomic nuclei dissolve into a surreal quantum soup. Here, in this alien realm, the distinction between the very small and the very large blurs, giving rise to phenomena that could bridge Einstein's gravity with the quantum world for the first time. Take the neutron star Pulsar 1748-2446 AD, spinning an astonishing 716 times per second. According to classical physics, its surface should be flinging off material at nearly a quarter the speed of light, yet somehow it holds together. The secret may lie in its crust, a crystalline lattice of neutron-rich material just a few hundred meters thick, where the pull of gravity is so strong it warps the quantum behavior of particles. Under these conditions, space itself might become granular, with tiny fluctuations in the fabric of reality altering how the star rotates. Picture a ballerina spinning on a floor made of sand. Every grain shifts slightly under her weight, subtly changing her motion. Now imagine the floor is space-time, and the ballerina is a city-sized star. The most tantalizing clues come from glitches, sudden speed-ups in neutron star spins that defy conventional explanations. When the crust of a neutron star cracks under unimaginable pressures, the resulting vibrations could be revealing quantum gravity in action. Some theories suggest these tremors create microscopic black holes within the crust that wink in and out of existence, their fleeting gravitational influence nudging the star's rotation. Others propose that the crust's neutrons form Kuiper pairs, behaving like a superfluid whose vortices interact with spacetime in ways that transfer angular momentum unpredictably. But the real revolution lies in what this means for unification physics. Neutron stars might be nature's perfect laboratories for testing theories like loop quantum gravity or string theory, ideas that remain purely mathematical elsewhere. When gravitational waves from colliding neutron stars were detected, subtle discrepancies in the signal hinted at quantum corrections to Einstein's equations, as if spacetime itself had a pixelated structure on the smallest scales. The implications ripple far beyond stellar corpses. If quantum gravity leaves fingerprints in neutron star dynamics, it could reshape how we model everything from black hole mergers to the Big Bang's first moments. These ultra-dense objects aren't just relics of dead stars, they're cosmic Rosetta Stones, holding the key to decoding how the universe truly operates when gravity and quantum mechanics collide. And with every glitch, every gravitational wave, they're sending us messages from the edge of known physics. Black holes aren't just the universe's heavyweight champions. Some might be its oldest hidden relics, lurking in the shadows since the dawn of time. Primordial black holes, hypothetical remnants from the first chaotic seconds after the Big Bang, could be drifting through galaxies like cosmic ghosts, their presence betrayed only by the faintest gravitational whispers. Unlike the massive black holes formed from collapsing stars, these ancient anomalies might be as small as an atom yet denser than a mountain, packing the mass of an asteroid into a space tinier than a pinpoint. And if they exist, they're rewriting the rules of gravity right under our noses, or rather, right through our telescopes. Imagine a black hole no wider than a molecule but with the gravitational pull of Mount Everest. Now picture thousands of them sprinkled invisibly across the Milky Way, their minuscule event horizons too tiny to emit detectable radiation, yet their gravity subtly warping the paths of nearby stars and gas clouds. Astronomers have spotted strange gravitational anomalies, stars wobbling without visible companions, rogue planets accelerating inexplicably, even entire star clusters moving as if tugged by unseen hands. Traditional dark matter explanations fall short, but primordial black holes, they fit like missing puzzle pieces. One tantalizing clue comes from microlensing surveys, where telescopes watch for the brief brightening of distant stars as unseen objects pass in front of them, bending their light like a cosmic magnifying glass. Some of these events last mere hours, far too short for ordinary stars or planets, but perfect for tiny, dense objects like primordial black holes. Then there's the case of the Hyade star cluster, where stars exhibit odd, synchronized motions that suggest an invisible interloper. Perhaps a primordial black hole is weaving through them like a gravitational ninja. The implications are staggering. If these ancient black holes are real, they could solve multiple cosmic mysteries at once. Some might be the elusive dark matter we've hunted for decades, their collective gravity shaping galaxies without emitting light. Others could explain bizarre gravitational wave signals that don't match typical black hole mergers. What if we're hearing the collisions of primordial black holes from the universe's infancy? Even more radical, some might still linger in our solar system, their feeble gravity occasionally nudging comets or asteroids onto unexpected paths. But the most mind-bending possibility. These black holes could be time capsules, preserving conditions from the first moments of creation. Their extreme density might trap quantum fluctuations from the Big Bang itself, offering a window into physics far beyond our current understanding. Every unexplained gravitational flicker, every anomalous star movement could be a breadcrumb leading us back to the universe's wild, untamed beginnings. The cosmos isn't just hiding its secrets in distant galaxies. They might be floating right past us, invisible and ancient, rewriting gravity one pinprick at a time. Gravitational waves were already one of the universe's most astonishing revelations, ripples in space-time from cataclysmic events like black hole mergers. But now, scientists have discovered something even more extraordinary. These waves aren't solitary pulses. They're followed by faint, ghostly echoes, like the reverberations of a bell struck in a cosmic cathedral. These secondary ripples, detected through painstaking analysis of data from observatories like LIGO and Virgo, suggest that space-time itself doesn't just bend under extreme violence, it vibrates, ringing with the memory of collisions long after the initial shock has passed. Take the merger event GW 150,914, the first gravitational wave ever detected. When researchers re-examined the signal with new, ultra-sensitive algorithms, they found faint secondary peaks trailing the main burst, tiny fluctuations in the data that shouldn't exist if space-time simply snapped back into place. Instead, it's as if the fabric of reality briefly shuddered, sending out whispers of the original collision like echoes in a canyon. These ring-down signals aren't mere noise. They match theoretical predictions of how a newly merged black hole settles into its final form, oscillating as it sheds excess energy. It's the universe's way of sighing after a monumental effort, its gravitational afterglow revealing secrets about the most violent events in existence. What's truly revolutionary is what these echoes can tell us. The frequency and decay rate of these ripples act like a cosmic fingerprint, encoding information about the merged object's mass, spin, and even shape. Some signals hint at black holes with hairs, subtle deformities in their event horizons that defy the classic no-hair theorem. Others suggest the presence of exotic physics, like remnants of string theory's extra dimensions or quantum gravity, effects normally invisible to our instruments. Imagine listening to a bell's ring and deducing not just its size, but the material it's made of and the force of the strike that set it singing. That's the power of gravitational echoes. They turn collisions into cosmic diagnostics. Yet the implications stretch far beyond black holes. Neutron star mergers, like the landmark event GW 170,817, also leave behind ripples, but with a twist. Their echoes carry hints of the ultra-dense matter left in the wreckage, offering clues about the mysterious state of matter at densities so extreme, atomic nuclei dissolve into quark soup. Some theorists speculate these echoes might even reveal gravastars, hypothetical objects where black hole singularities are replaced by bubbles of dark energy, their exotic physics ringing through space-time in unique harmonics. The most tantalizing possibility that these echoes could be evidence of ancient collisions we've long missed. Gravitational wave detectors have only been operational for a few years, but the universe has been echoing with mergers for billions. Advanced algorithms are now sifting through archival data, searching for the faintest traces of these after ripples. If successful, we might uncover a hidden catalog of forgotten cosmic crashes, their stories preserved not in light but in the lingering tremors of space-time itself. This discovery doesn't just add another layer to astrophysics, it changes how we listen to the universe. We're no longer just catching the shouts of cosmic violence, we're tuning into its whispers, the quiet aftermath that holds the deepest secrets. And with every echo decoded, we're learning that space-time isn't just a stage for the universe's drama. It's an active participant, humming with the memories of everything that's ever shaped it. What if the universe's deepest secrets aren't hidden in the vastness of space, but in its very fabric, or rather, the lack thereof? The holographic principle, one of the most radical ideas in modern physics, suggests our three-dimensional reality might be nothing more than a shadow cast by information encoded on a distant two-dimensional surface. It sounds like science fiction, but this mind-bending theory could leave fingerprints on something surprisingly tangible: the motion of celestial bodies. Imagine gravity not as a force radiating from masses, but as a kind of cosmic pixelation, a projection of data from the universe's hidden edges, subtly altering how stars and planets dance through the void. The first clues emerged from black hole physics, when scientists calculated the maximum entropy a black hole can contain. They found it scales not with its volume, but with its surface area, as if all the information inside was somehow smeared across its event horizon. Extend this idea to the entire cosmos, and you get the holographic principle. Every particle's position, every planet's orbit, might be determined by quantum bits living on a remote boundary we can't see. If true, this would mean the trajectories we observe are like the movements of characters in a video game, their paths dictated not by local physics, but by code written on a faraway screen. So how could this affect real-world orbits? One startling possibility involves entanglement entropy, a measure of how quantum particles share information across space. In holographic models, this entropy creates subtle corrections to gravity's equations, introducing tiny deviations in how objects attract one another. Picture the Moon's orbit around Earth. Newton's laws predict its path with exquisite precision, but if the holographic principle holds, there might be minuscule, fractal-like fluctuations in its trajectory, as if space-time itself has a resolution limit. These deviations would be vanishingly small, perhaps just nanometers over lunar distances, but future ultra-precise laser-ranging experiments could detect them. Even wilder implications emerge when considering cosmic scales. Galaxy rotation curves, which famously require dark matter to explain, might instead reflect holographic corrections to gravity at vast distances. The extra pull we attribute to invisible matter could actually be the universe's underlying code asserting itself like a glitch in the simulation, nudging stars off their expected paths. Some theorists even speculate that the puzzling alignment of certain quasar polarizations across billions of light years, the so-called axis of evil, could be a relic of the 2D boundaries' preferred directions imprinting on our 3D projection. Critics argue these ideas stretch credibility, and they're not wrong. Testing them requires precision beyond current technology. Yet the mere possibility ignites a revolution in how we view celestial mechanics. If the holographic principle shapes motion, then every orbit, every galactic spiral, is more than just gravity's handiwork. It's a message from the universe's hidden operating system, written in the language of falling apples and orbiting pulsars. And that's the beauty of this discovery. It turns the cosmos into a cosmic detective story, where the clues aren't just in the stars, they're in the spaces between what we see and what might truly be. These 38 discoveries aren't just rewriting textbooks, they're tearing up the entire playbook of celestial mechanics. For centuries, we've navigated space missions, predicted eclipses, and modeled galaxies using equations we thought were set in stone. Now, every calculation, every simulation, every assumption about how objects move through the cosmos demands a second look. Take something as routine as plotting a spacecraft's trajectory. Engineers have long relied on Newton's and Einstein's laws to slingshot probes around planets with pinpoint precision. But what if dark matter currents or quantum foam fluctuations subtly alter those paths in ways we've never accounted for? Suddenly, missions to Mars or the outer solar system might need entirely new error margins or even new propulsion strategies to stay on course. The ripple effects extend far beyond practical astronomy. Cosmologists are staring down a cascade of questions. If rogue planets accelerate inexplicably, could entire galaxy clusters be moving under forces we've yet to name? If neutron star glitches hint at quantum gravity, does that mean the universe's expansion isn't just driven by dark energy, but by space-time's granularity itself? Even the search for extraterrestrial life faces new variables. Habitable zones around stars were once thought to be static bands now, with orbit-flipping planets and resonating exomoons. A world could spend millennia in the sweet spot for liquid water, only to be hurled into deep freeze by a gravitational hiccup we didn't see coming. The tools to unravel these mysteries are already in our hands and on the horizon. Next-generation telescopes like the Vera Rubin Observatory and the James Webb Space Telescope aren't just sharper eyes, they're time machines capturing snapshots of cosmic motion across billions of years. AI-driven simulations trained on these observations can recreate scenarios no human mind could piece together, testing how dark matter flows might sculpt galaxies or how primordial black holes could lurk undetected in our solar system. And gravitational wave detectors, now sensitive enough to catch spacetime's faintest whispers, are poised to uncover collisions between objects we've yet to classify. Perhaps the most thrilling prospect isn't just filling gaps in our knowledge, it's discovering entirely new categories of physics. Every anomaly, every deviation from expectation could be a doorway. What if hypervelocity stars with curved paths aren't just oddities, but evidence of higher dimensions warping local gravity? Could the holographic principle's subtle fingerprints on planetary orbits reveal that space-time itself is pixelated? The universe has spent centuries showing us a fraction of its repertoire. Now, with these 38 revelations as our guide, we're finally tuning into the full symphony, and the music is stranger, wilder, and more beautiful than we ever imagined. As we've journeyed through these 38 cosmic revelations, one truth becomes clear. The universe doesn't just follow rules, it reinvents them. Think about that for a moment. The same night sky that once seemed so predictable, so clockwork in its motions, is actually a stage for gravitational improvisation, quantum whispers, and celestial rebellions. From rogue planets accelerating without cause to neutron stars pulsing with quantum secrets, every discovery peels back another layer of the cosmos's playbook, revealing just how much we've yet to learn. Consider this: every time we've assumed we've cracked the code of celestial motion from Newton's apple to Einstein's spacetime, the universe has responded with a wink and a new puzzle. Take galactic bars spinning faster than dark matter should allow, or magnetars bending orbits with magnetic might. These aren't just anomalies, they're cosmic breadcrumbs, leading us toward deeper truths about gravity, matter, and the fabric of reality itself. Even the emptiest voids, stretching space itself apart, remind us that nothing in the universe is truly passive. Every corner, from the densest black hole to the most barren expanse, hums with hidden activity. What's thrilling isn't just the scale of these mysteries, it's how they reshape our role as observers. Astronomy is no longer just about mapping the heavens, it's about decoding a living, evolving dialogue between matter and motion. The same gravitational waves that ripple from colliding black holes also leave echoes, as if space-time itself has a memory. The same quantum foam that might tweak spacecraft trajectories could be quietly sculpting the orbits of distant worlds. Every time we point a telescope or fine-tune a detector, we're not just collecting data, we're eavesdropping on a universe that's still introducing itself. And that's the real invitation here. These 38 discoveries aren't endpoints, they're gateways. For every hypervelocity star with a curved path, there's a hidden force we've yet to name. For every flipping exoplanet, there's a gravitational dance step we're only beginning to recognize. The cosmos isn't just challenging our models, it's daring us to dream bigger. Whether you're a professional astronomer passing data or a stargazer lying on a backyard blanket, the message is the same. Look up, stay curious, and embrace the beautiful, bewildering fact that the universe will always have one more surprise up its sleeve. The next revelation, it's already out there, waiting in the dark, not just in the stars, but in the spaces between.